Welcome back. So last time we talked about homogeneous solutions, which means we're solving where our B vector was, or in other words, our all right vector was all zeros. Well, non-homogeneous is actually anything that it's not the homogeneous solutions. So it's the solutions when I have something besides that. So as it says, like right here, a non-homogeneous solution has many solutions. The general solution can be written as a parametric vector form as one vector plus an arbitrary linear combination of vectors that satisfy the corresponding homogeneous. Okay, well, what does that mean? That means in order to solve the non-homogeneous, we actually solve the homogeneous, and then it's something a little bit extra. So often we break these things down by focusing on the homogeneous instead of the non-homogeneous. So an example is consider the line y equals 3x, and then the yellow line, y equals 3x plus 5. How are they the same? How are they different? This is a homogeneous problem because notice the zero vector is a solution of this. It's not over here. So let me write that in. Let me point. This is homogeneous. Pardon my handwriting. This one is non-homogeneous. So this is a homogeneous versus a non-homogeneous solution, and that helps us begin to realize how we can actually examine these things and understand them a little bit better. So similarly, we just shifted it. Well, guess what? Non-homogeneous are just shifts. So let's look at this. Suppose that B is 7, 1, negative 4. Well, to find the solutions, I could set this up as an augmented matrix like this. And if I wanted to do that, I can go ahead and solve it. All right, so go ahead and pause the video and solve this specific system of equations. And then I'm going to show you how it ties back. So go ahead and pause the video. All right, so if you did that, you go through the same steps. Notice it's the exact same steps as we did before. The only thing that's different is now we have things that are changing these values. So now we're just messing around with this column. Everything is the same. Ooh, that's not pretty. Everything in this portion is all the same as it was when we did this previously for the homogeneous version of the exact same matrix. Our A was exactly the same, but now we have a different thing. So we keep going through our solutions, same exact steps. Notice my row reduction steps are exactly the same because I don't care about what's happening in that far one. Now, when we get to here, again, this is an important portion because this is row echelon form. Because I have no pivot and my last row is all zeros, it means I have a solution to this. Now, that's really important. If for some reason this value right here was anything besides 0, then I would not have a solution. So it has a solution, so we keep going on. And we get to this. Okay, so we keep solving. Again, same row reduction steps as we did before. We get to this phase. Now again, there's more potential here of having a fraction in this spot than when it was zeros, so we got to keep that in consideration. What does this mean? Well, let's write this as actual system of equations. Remember, this is going to be x1 minus 4/3 x3 equals -1, and then x2 equals 2. Or in other words, x1 is equal to -1 plus 4/3 x3. This looks very similar because notice it looks almost identical, except x3 is still free, and we just modified by adding -1 here and 2 right here. So what does that mean? Well, that means that my solution vectors, x1, x2, x3, or it looks like this, now comes a little bit of a trick. I have to break this into the two vectors, the one that includes x3 and the one that includes constants. Well, notice that this right here, I'm going to circle the second vector, it is the solution to our homogeneous system. So we have some amount of shift. It's not exactly what I'm going to point this out. Some people think it's always just your B vector. It's not your B vector, but it is going to be something offset by this value. So what does that mean? I get here, and I could have written this instead. Sorry, I could have written this as instead, I clicked that one too many times. As this is some new vector, we'll call it U plus x3 times that vector V, which was still my homogeneous solution. So whenever we solve our homogeneous solutions, it actually opens up the door, so we only have to find that little bit extra for the non-homogeneous solutions. So what are the final takeaways you can take from this section? Well, a key one is this theorem. If there's any vector ax equal b is consistent, meaning it has a solution for b, and let p be a solution of that, well then that is always going to be p. So it's a solution plus the homogeneous solution. So it's always some single value. All you have to do is find one solution to my ax plus b, and then I just add that solution onto the homogeneous solution. So this is why we like homogeneous solutions. So we're translating, you want to call that shifting, but remember it's not the same because we're in higher dimensions potentially. We're geometrically translating v by p, which we'll get to an idea that we're going to get to in our coming sections. Similarly, these vectors are parallel. Okay, that's really nice. So we're simply creating a new plane or vector or whatever structure that we're talking about, because it depends on which dimension we have, that we then get to use. I hope that helps. Let me know what questions you have, and good luck.